So as I promised in class, I wanted to go over the derivation for the energy of a simple harmonic oscillator. Doing it in the video would eliminate taking up the class time for it. And it gives us a good way to really think about what's happening as a mass on a spring oscillates back and forth, if we think about it from the viewpoint of the energy transitions that are happening. So we go back to our very basic expression for the energy of a system can be a combination of the kinetic energy and the potential energy. And if you forgot, the potential energy of a spring is 1/2 kx squared. Now, for our simple harmonic oscillator, I wanted to remind you of how we express the x position of the oscillator and its velocity. And so we're going to take these two expressions and substitute them into our energy expression. Okay, so I just wanted to make a comment about what I just did. I don't want to have to keep writing omega t plus phi, so I just put the empty parentheses, and with the understanding that what's inside of them is the omega t plus phi, because eventually that whole thing is going to disappear anyway. So what I've done is I've substituted in for the velocity term, our velocity, and we square that, and then the same thing for the x, and we square that. Now when we square it, we're going to get rid of that pesky negative sign for one. All right, so now we have a term that involves the sine squared and the cosine squared, and it would be really nice if we could make these similar, have similar coefficients, because we know that sine squared plus cosine squared is equal to 1. And then we would be able to get rid of those terms. Well, it turns out that we can do that because we could substitute in here for the omega squared. So omega squared would be the same thing as k over m. And so if we do that, what that is going to do is our mass is going to cancel out, and we're going to have 1/2 ka squared in both of these terms. And then if we factor that out, we have the term sine squared plus cosine squared, which is just equal to 1. And so we come to the conclusion that the total energy can be expressed as 1/2 ka squared. That's really comes in handy as we're trying to figure out, for instance, how fast the object is moving if we know what its x coordinate is. Let's look at this result from the point of view of energy. If you think about it, it's saying that the total amount of energy would be the same as the potential energy that the mass on the spring has when it's at its amplitude, its maximum amplitude. Well, that makes sense because we already talked about the fact in class today that when it's at its maximum amplitude, the velocity is 0. So it actually is true. So we can actually quantify the total amount of energy that our mass on a spring system has by the potential energy it would have at its maximum amplitude. And like I said, if we use this expression, we can manipulate it in different situations where we, again, want to say, oh, if the position of the mass is at half the amplitude, how fast is it moving? And we could actually substitute in for x 1/2 the amplitude and then solve for the velocity. It becomes pretty easy to do that. Now, the other thing that I wanted to look at with reference to this expression is just thinking more about what happens in terms of the transition of energy as our mass on a spring is oscillating. So this is going to involve some memory for you. So if we have the vertical axis representing energy and the horizontal axis representing x, I want to remind you that the potential energy function for our mass on a spring is 1/2 kx squared, and so it just looks like a parabola. And now what I could do is I could say, okay, let's imagine that we are allowing our oscillator to only have a certain amount of energy. So if we represent this is the total energy, and that's a horizontal line. What it means is that, okay, here, this point right here, which if we go down to here, would represent x equal a, and this would represent x equal minus a. And as what that says is then, if you think about it, that location is where the potential energy intersected with the total energy. And so exactly, at that location, this would represent the point where the oscillator was at its maximum amplitude and all of its energy was in potential energy. And same thing here, when it's at its maximum compression, all of its energy is in potential energy. If we think about that, then what we're saying is that from the horizontal axis to our potential energy function, anywhere on this graph between these two turning points would represent the amount of potential energy it has, and then the difference between that and the total energy would represent the kinetic energy. And so think about what is happening as our object oscillates back and forth. If I start off at a maximum displacement of A, it has all potential energy, but then I release it, and as it starts moving back towards equilibrium, it's going to lose potential energy and gain kinetic energy. At the equilibrium location, it actually has 0 potential energy and has the maximum kinetic energy. All of its energy is in kinetic. And then as it proceeds to start to compress, we see the transition of that kinetic energy going back into potential energy. And then when it reaches its maximum contraction, it has, or compression, it has all of its energy back in potential. So literally our object is moving between these 2 points, but as it does, the energy is being transferred between potential and kinetic the whole time. And those always are going to be adding up to the total energy. This is a really helpful thing to think about as we try to understand this motion in a little bit more detail.